Envision an infinitely expansive, completely vacant, and sterile room, extending in all directions, devoid of any dust particles and impervious to any penetration of light. Now, picture a flashlight within this space. It may seem splendid, but there is a slight inaccuracy. The visual scenario should be clarified. If observed from outside the room, neither the flashlight nor the light it emits would be visible. Paradoxically, light possesses invisibility as one of its well-understood properties. We only perceive it when it enters our eyes. Light that simply passes by, without reflecting off anything, remains unseen to us. Even with a second light source, we might observe the flashlight, but not its emitted light. Rays of light, even the most intense ones, effortlessly pass through each other, as if encountering no obstruction in their path. Keep this in mind. Now, picture a flashlight shining directly into our eyes. As we gradually move backward, the reflector will appear progressively smaller until it transforms into a dot. As we continue moving away, that dot will grow dimmer and dimmer. When the distance between our eyes and the flashlight reaches 10,000 kilometers, the faint cloud will vanish completely. However, this scenario applies specifically to the human eye. The frog's eye, being several times more sensitive than the human eye, introduces a significant variation in the experiment's outcome. For a frog observer moving away from the electric flashlight, there is no moment when it completely loses sight of the light. Instead, the frog begins to witness an engaging pattern. The flashlight starts to blink at uneven intervals. These intervals expand as the frog moves farther away. At a distance of 100 million kilometers, the frog, on average, perceives only one flash of light per day. Nevertheless, each flash remains as bright as any other throughout infinity. This intermittent flicker demonstrates a limitation to the uniform stretching of light. Each flash observed by the frog results from a photon impacting the retina of its eye. As the frog distances itself from the flashlight, the photons themselves do not weaken. Rather, the beam of light weakens because the free space between the photons expands. When a frog perceives nothing, it's not due to the light entering its eyes being too weak, but rather because no light enters its eyes. This characteristic of appearing only in discrete sizes is known as quantization. An individual unit of light, a photon, is referred to as a quantum. Quantum theory derives its name from this specific property, attributing it to all measurable physical quantities. In physics, there are no measurable continuous quantities. Contrary to what surrounds us appearing continuous, it is, in fact, not continuous. The content of this video is drawn from the book The Fabric of Reality by British theoretical physicist David Deutsch. Deutsch articulates his fundamental view of the universe, albeit somewhat confusingly, likely due to his identity as a scientist rather than a writer. Therefore, we will directly quote from the book and supplement it with information from alternative sources for the sake of a comprehensive and accessible presentation. Deutsch's ideas are notably intriguing. While this book is likely to stir some controversy within scientific circles, the video itself will probably focus less on that aspect and more on the compelling idea that we almost certainly inhabit a multiverse. Phrases like multiverse, parallel realities, and alternative worlds are commonly used in everyday language, often applied when discussing improbable events, such as imagining oneself as a billionaire in one of the parallel universes. However, let's be honest. Very few people take the concept of a multiverse seriously, and many are unfamiliar with its implications in the realm of physics. The idea of multiple universes is articulated differently in various physical concepts, each with its own validity. The video will delve into the many worlds interpretation of quantum mechanics, which, as a direct and relatively straightforward consequence, provides us with a fresh perspective on the world. This perspective is so novel that as scientists sought to comprehend the laws of quantum mechanics, they grappled with explaining their observations. The desperation to understand was such that discussing anything beyond equations is now considered somewhat unfavorable among specialists in quantum theory. David Deutsch, however, rejects this instrumental approach to physical theory. From Deutsch's perspective, the usual desire to not only predict and use, but to understand is commendable. Interestingly, quantum mechanics is the most tested and successful theory in the history of science, and its practical application is evident in semiconductor electronics, the very technology that allows you to watch this video. Despite its success, the intriguing aspect is that we still lack a full understanding of quantum mechanics. While Einstein's general theory of relativity has enlightened us about the curvature of the space-time continuum, quantum mechanics remains a mystery. All we have are interpretations and arguments about which interpretation is more accurate. The mystery deepens at the quantum level, and you've probably heard of the double-slit experiment, a favorite subject of Richard Feynman. According to Feynman, scrutinizing the implications of this experiment encapsulates the essence of quantum mechanics. Let's briefly illustrate the experiment. Take a foil with two small slits spaced 1/5 millimeter apart. Place a screen behind the foil. Shine an ordinary laser on the slits. If the light were propagating in a straight line, we would expect to see two bright stripes with sharp boundaries spaced 1/5 millimeter apart in this experiment. However, the actual outcome of the two-slit experiment is quite unusual. Instead of two bright stripes with sharp boundaries, we observe multiple bright and dark stripes with no clear distinctions. Now, consider what happens if we cut two more slits of the same kind between the existing two, creating 4 slits, spaced 1/10 of a millimeter apart. Intuitively, one might expect the pattern to be similar, but the reality is quite different. The shadow produced by the 4 slits does not simply appear as a combination of two slightly shifted shadows from the original 2 slits. Instead, it exhibits an entirely different structure. Notably, there are areas like point X that were illuminated when there were only 2 slits, but cease to be illuminated when 2 additional slits are introduced. Intriguingly, the removal of these additional slits results in the re-illumination of point X. This phenomenon raises questions. Something is passing through the second pair of slits, interfering with the light from the first pair and preventing it from reaching area X. But what is causing this interference? It becomes evident that whatever is causing the interference is within the light beam itself. This mysterious factor is consistently present in the light beam, but absent outside of it. The phenomenon observed in the experiment indicates that light is either reflected, transmitted, or blocked by elements that reflect, transmit, or block it. The seemingly logical conclusion is that the interfering factor is the light itself. Photons from one slit interfere with photons from other slits. However, a paradox arises if we consider that photons, as traditionally believed, do not interact with each other. The question arises, how can they interfere? To further investigate this question, the experiment is performed with a laser releasing only one photon at a time. Surprisingly, the result remains the same. Even in the case of single photons, there is not a single instance of them hitting point X when all 4 slits are open. However, closing 2 slits causes the flashes to resume at point X. The idea that the photons split into fragments, change their trajectory through the slits, and reunite is ruled out. Placing detectors at each slit confirms that even 2 detectors are never triggered at the same time. So what is this invisible and intangible factor that interferes with the original photon? It remains undetectable by instruments and is a mystery requiring further investigation. In examining the behavior of a single photon passing through the apparatus, it becomes apparent that the photon traverses one slit and is subsequently influenced, causing it to deviate from its expected trajectory. This impact is contingent on which other slits are open. Surprisingly, the objects affecting the photon pass through the other slits and mimic the behavior of photons, despite being invisible. One might conceptualize these as shadow photons, only indirectly detectable through their influence on real photon. Every real photon is seemingly accompanied by shadow photons. When a photon passes through one of the 4 slits, some shadow photons pass through the remaining slits. Notably, the number of shadow photons appears to far exceed that of real photons. Deutsch and colleagues propose that there is no upper limit to the number of shadow photons, with a minimum estimate of 1 trillion shadow photons per real photon. Delving into microscopic interactions, the question arises, what occurs when shadow photons encounter a light-tight barrier? Evidently, they come to a halt. This conclusion is drawn from the cessation of interference when a light-tight baffle is introduced in the path of shadow photons. However, the underlying mechanism remains enigmatic. It's implausible that shadow photons are absorbed by the actual atoms of the baffle, as the expected number of shadow photons would lead to the vaporization of the baffle, a phenomenon detectable through various means. The peculiar aspect is that shadow photons do not interact with real atoms, yet the baffle affects both real and shadow photons in a similar manner. It stops them. However, shadow and real photons affect the barrier differently. It is noteworthy that shadow photons seemingly have no effect on it, but nevertheless they stop. Hence, there is a corresponding shadow partition at the location of the material partition. This is an inescapable conclusion. Without much effort, it becomes apparent that this shadow partition consists of shadow atoms, recognized as duplicates of the real atoms in the partition. Each real atom has many duplicates. Even in a weak fog, the total density of shadow atoms is more than enough to impede the movement of a tank, let alone a single photon, if these atoms could affect it. Some might argue that these conclusions are too far-reaching, given that we are talking about the microcosm. How can one extrapolate entire parallel universes based on photon interference alone? Light particles, or quanta of light, may not possess mass, but the presence of an interference pattern on fullerene molecules challenges this notion. Fullerene, a form of pure carbon, is essentially a classical object. Simply put, particles are arranged in parallel universes, where, within each universe, they interact much like they do in the real universe. However, the influence of each universe on the others is minimal. This influence becomes evident through the phenomenon of interference. Thus, a chain of inference emerges, starting from peculiar shadow patterns and concluding with the concept of parallel universes. At each step, it becomes apparent that the observed object behaviors can only be elucidated by considering the existence of unseen objects and their properties. The fundamental idea is that the interference of a single particle negates the possibility of the sole existence of the real universe that surrounds us. Despite this, the theory of a multiverse hasn't gained widespread acceptance among physicists for an extended period. Why? The apparent grandiosity of its conclusions makes some physicists question why we can't simply attribute the behavior of photons to an assumption that they act as if colliding with imperceptible objects. Why must we go further and embrace the theory asserting the actual existence of these invisible objects? The tangible photon is real, and the shadow photon represents the potential but unrealized behavior of the real photon. Quantum theory delves into the interaction between the real and the potential. However, David Deutsch argues against leaving things as they are, saying that the potential cannot interact with the real. Objects that do not exist cannot change the course of existing objects. If a photon deviates from its path, some factor must influence it. It cannot be that an actual event, such as the appearance and detection of a real photon, is caused by an imaginary event, something the photon could have done but didn't. As already mentioned, interference is not only characteristic of photons. Quantum theory predicts, and experiments confirm, that interference occurs with any particle. Consequently, every real electron is accompanied by a significant number of shadow electrons, and every real neutron has a significant number of shadow neutrons, and so on. This means that reality goes beyond the visible, and much of it remains invisible. The aggregate of shadow particles can be called a parallel universe, since these shadow particles are influenced by real particles solely due to the phenomenon of interference. Going even further, the shadow particles are separate from each other, mirroring the separation between the universe of real particles and them. In essence, they do not form one homogeneous parallel universe, much larger than the real universe. Instead, they form many parallel universes. Each of these parallel universes is similar in composition to the real universe and obeys the same laws of physics. However, they differ from each other in the arrangement of particles. Let us return to the experiment with two slits. If detectors are positioned near each of the slits to capture a photon passing through both slits, the quantum will consistently be detected emerging from only one slit, never both. This is consistent with the inherent indivisibility of the quantum. The interference pattern on the screen suddenly disappears, replaced by a normal distribution of the two fringes. One could argue that this result was expected, given that at the atomic level, measurement is inherently about interaction. In trying to detect a slit through which a photon passes, the detector inevitably affects it, changing its behavior. Fair enough. However, even if there is only one detector near one of the slits, the quantum passing through the other slit is not detected, and there is no interference. Surprisingly, it seems as if the quantum somehow recognized that it was being measured at the other slit and decided not to interfere. In fact, the very possibility of being able to tell which slit the photon chose deprives us of the ability to observe interference. It seems almost mystical. The observer influences the universe through the act of observation. The classical interpretation of the founding fathers of quantum mechanics played a role in the development of these ideas. The classical interpretation, also known as the Copenhagen interpretation, stands as the predominant perspective among scientists who opt for any explanation. Advocates of this interpretation categorize the world into quantum observable objects and classical measuring devices, which seems somewhat peculiar. In this framework, a quantum object like our photon, before measurement through the slits, exists as a probability wave, a superposition of quantum states. However, the moment this probability wave interacts with a classical system, such as a screen or a detector, it promptly collapses into a particle at a specific location. In other words, until observed, the photon exists as a wave, but upon measurement, it transforms into a particle. Within the Copenhagen interpretation, this phenomenon is termed the collapse of the wave function. Einstein expressed his skepticism, stating, "I'd like to believe that the moon is still there, even if we're not looking at it." Countless iterations of the double-slit experiment have been conducted in various ways to restore common sense, yet all efforts have proved futile. The implications appear perplexing, to say the least, within the framework of the Copenhagen interpretation. Despite having garnered the largest number of supporters, David Deutsch contends that, in reality, no one among scientists has truly believed in it for a considerable period. In 1957, the American physicist Hugh Everett was the first to clearly articulate that quantum theory describes a multiverse. During that era, his ideas didn't receive much attention. Many experts now agree that the many worlds interpretation resolves most questions about the peculiarities of the subatomic sphere. Hugh Everett's interpretation asserts that interference does not actually disappear in observation. The notion that observation destroys interference is wrong for three reasons. First, it assumes a psychokinetic effect of the conscious observer on fundamental physical phenomena, which does not exist. Second, interference does not disappear. It just becomes harder to detect because it requires precise control over a larger number of particles. Third, the effect of any photon on the surrounding space, depending on the trajectory it chooses, produces the same result as observed. And most importantly, am I really a billionaire in some parallel universe? First of all, what does that mean I am? It's not me anymore. For comparison, let's take the analogy of identical twins. Genetically, they start out as the same zygote. However, is it possible to claim that your twin is you, especially as the differences between you accumulate over time? Furthermore, the exact number of universes remains unknown. If universes are not infinite, then highly improbable events may not occur in a multiverse. On the other hand, if there are an infinite number of universes, then all conceivable events within physics occur in the multiverse. This includes scenarios such as a universe in which the sun exploded because all of its atoms rushed haphazardly toward the center, although this event exists on an incredibly unlikely probability branch in the multiverse. It does occur. Technically, there are an infinite number of universes where the sun exploded, but this infinity is incomparably smaller than the infinity of universes where the sun feels normal. Both of these universes are infinite in number, and all of them differ in density. Here is a simple example. The infinity of natural numbers exceeds the infinity of even numbers. The many worlds interpretation, in contrast to the Copenhagen interpretation, asserts the fully quantum nature of the entire world, proving to be more consistent than the quantum classical world proposed by Copenhagen. What is remarkable about the many worlds interpretation is the absence of a mystical observer causing the wave function to collapse. Instead, there is a continuous splitting process called decoherence. In the double-slit experiment, photons pass through the slits in every conceivable way, simultaneously. When we measure a photon, entanglement occurs, leading to splitting into different versions, each of which is engaged in measuring the photon in all potential states. This leads to scattering along the branches of probability within the multiverse. One might wonder, what is measurement, and how does the universe realize that the photon has been measured and it is time to separate? In this context, the laws of entropy, which serves as a measure of irreversible energy dissipation, become relevant. Any irreversible interaction qualifies as a measurement, and an observer does not need to have intelligence for that. Consequently, the moon exists even in an unobservable state, given its status as a vast macrosystem experiencing continuous, irreversible interactions. When an observer measures a quantum system in superposition, entanglement occurs, causing the observer to collapse into every conceivable version of itself. This creates the appearance of superposition to another outside observer. Subsequently, a second observer observing the first observer becomes entangled and also splits into different versions of itself. This process continues, encompassing the entire universe, and is called decoherence. And what we observe as collapse is nothing other than simply our inability to untangle the object and the environment with which it is entangled. Any solid is made up of a collection of atoms, which in turn are made up of electrically charged particles. But from classical chaos, no aggregate of charged particles could remain stable under classical laws of motion. The positively and negatively charged particles would simply snap out of their places and collide with each other. Only strong quantum interference between different trajectories of charged particles in parallel universes prevents such catastrophes and makes the existence of solid matter possible. The challenge in extending interference to the moon lies in its complexity. While we can induce interference in molecules, achieving the same with a massive cosmic body, like the moon, proves daunting due to its sheer size. The principle of superposition demands absolute isolation of the quantum system from external influences. To place the moon in a state of superposition, all photons capable of reflecting off its surface must be eliminated. The presence of even a single photon could result in an irreversible interaction, causing the collapse of the superposition state. To achieve interference, free conditions, cooling the satellite to absolute 0 Kelvin is necessary, as any higher temperature would cause the moon to emit photons into the environment. Absorption of these photons by any object would constitute an irreversible interaction. However, even if these stringent conditions are met, a single atom near the moon, influenced by its tidal forces, could change its trajectory and irreversibly measure it. The challenge of isolating quantum systems from the external environment is a central issue in constructing quantum computers. Despite this challenge, the consensus among experts is that the development of fully functional quantum computers is only a matter of time. Quantum computers have the capability to solve tasks in minutes or seconds that would take hundreds of billions of years for traditional computers. This is achieved by leveraging parallel universes. While classical computers perform operations sequentially, quantum computers execute tasks simultaneously through the phenomenon of superposition. For instance, in the case of Shor's algorithm, a quantum algorithm used to factorize a 250-digit number. The number of interfering universes would be on the order of 10 to the 500th power, an immensely vast quantity. David Deutsch proposes exploring explanations for how Shor's algorithm works without invoking the concept of parallel universes. I don't mean predictions of what the results of Shor's algorithm will be, since solving a few consistent equations is enough to do that. I am asking for an explanation when Shor's algorithm decomposes a number into multipliers, a number involving about 10/500ths of times more computational resources than can be seen in the visible universe. Where does that number get decomposed into multipliers? In the entire visible universe, there are only about 10 to the 80th power of atoms. The number is negligible compared to 10 to the 500th degree. Thus, if the visible universe were the space of physical reality would not even remotely contain resources sufficient to decompose such a large number into multipliers. Quantum computers exist today, but their performance falls short of expectations, requiring increased complexity to expand capabilities. However, increased complexity exacerbates the problem of isolation, as more complex quantum systems exhibit a higher degree of entanglement with their surroundings. This is why objects such as the moon, Schrödinger's cat, or even a speck of dust in the air cannot be in superposition for any measurable amount of time. The concept of time, familiar to all of us, is being re-evaluated in quantum theory, especially in the many worlds interpretation. For millennia, we have thought of time as a flowing river where the present moment is in constant motion toward the future, or that moments from the future pass by the present to become moments of the past. A closer look reveals a deep paradox in these ideas. It is as if there is only one truth in the present, and everything else is either an open future or a fait accompli of the past. Those of us who carefully observe the reality around us become fellow travelers of this true present. From the perspective of the particular observer, a particular moment does stand out, and that moment is labeled now, just as the observer's particular position in space is labeled here. However, even though space is three-dimensional and time is one-dimensional, no moment is objectively more privileged to be called now than any other moment. Similarly, no place in the universe has a superior right to be called here over all others. David Deutsch asserts that both here and now are subjective categories, lacking objective existence in nature. The notion of a present moment is considered an illusion, and space-time is often conceptualized as a block universe, where past, present, and future coexist in a frozen, four-dimensional block. Within this framework, there is no inherent motion. Everything in space-time is represented simultaneously. Moments, described as layers or snapshots of space-time, denote change or movement when their contents differ. Adopting such a model leads to the realization that consciousness exists across all moments when awake, and the various snapshots of the observer are not sequentially in a mysterious present. Each snapshot perceives its moment as now, with subjective awareness across all snapshots. Objectively, however, the concept of a singular present is non-existent. In this view, the flow or passage of time is not felt, but rather the difference between present sensations and present memories of past sensations is discerned, attributed to entropy. This perspective could be termed everyday philosophy if not for an experiment proposed by John Wheeler. At that time, it was only a thought experiment, but in 1999, physicists were able to put it into practice. We take a standard setup for launching single photons, but behind the partition, we install a barium borate beta crystal, thanks to which one photon is converted into two entangled photons of lower frequency. And because these photons are entangled, we can make measurements on one photon without interacting with the other. A little bit to the side, we'll position the lens so that it always combines the photons from the upper and lower slits in detector number 1. In this way, this lens erases the information about which particular slit the photon passed through. We will now make some measurements with another pair of entangled photons from both slits. Each will hit a different beam splitter, which is placed so that the photon has a 50% chance of reflecting down and a 50% chance of passing through. Those photons that will be reflected are combined, so there's no way to know which slit the photon went through. In other words, if detector number 4 registers a photon, we don't know which slit it flew through. In general, this is called a quantum eraser. Notice that detector number 2 can only detect photons from the top slit, and detector number 3 can only detect photons from the bottom slit. With a little patience, you'll be stunned by the results. Because here's what happens. When detector 2 registers a photon, detector 1, which registers its entangled twin, shows that it's a particle, not a wave. That's because we see two fringes, not an interference pattern. The same thing happens with detector 3. No surprise, because detectors 2 and 3 detect photons from specific slits. However, when detector 4 detects a photon, we already see an interference pattern that occurs on both detector 4 and detector 1. Due to the fact that it is not known which particular slit the photon traveled through, the interference does not disappear. So far, nothing new, isn't it? You haven't noticed anything. There's one detail that gives you the chills. And that detail is that the path to the detector is much shorter than the path to detectors 2, 3, and 4. So, a photon is always detected by detector 1, long before its entangled twin is detected by any other detectors. The most interesting thing is that an interference or 2 band pattern is formed at detector 1, even before the entangled photons reach the beam splitter. That is, the photon knows in advance whether its entangled double will be reflected from the beam splitter or will fly through. Take a minute to dig in. Repeated results from subsequent experiments suggest that measuring photons in the future seems to affect their state in the past. This implies a violation of causality. While various phenomena in physics such as binary black holes, wormholes, and early Big Bang moments hint at hypothetical violations of causality, one must question whether causality itself actually exists. The many worlds interpretation easily resolves these questions. In a block universe where everything is unchanging, one part of space-time can affect another, just as one part of a stationary three-dimensional object can affect another part. This view opens the door to a rethinking of causality and challenges our preconceived notions about the nature of time and influence in the universe. In simplified terms, if we know the position of one element in a fully assembled mosaic and understand the shapes of all the correctly assembled elements, we can predict the position of the other elements. However, the observed element is not necessarily the cause of the position of the other elements. It depends on how the entire mosaic was assembled. If the observed element was placed first, it is the cause. If another element was placed first, the position of the observed element is the effect, not the cause. In a scenario where the mosaic is created simultaneously, none of the positions of the elements are the cause or effect of the others. They are created simultaneously, according to predetermined rules. The determinism of physical laws in space-time events can be compared to the prediction of a correctly assembled mosaic. David Deutsch extends this idea by arguing that physical reality is not just a fixed block universe of space-time, but a diverse multiverse with infinite stories running parallel, overlapping, intersecting, and branching. However, if you envision all universes on a single timeline, forget it. Because in the multiverse, other timelines are also special representatives of other universes. This understanding initially surfaced in the 1960s through early studies of quantum gravity. However, it wasn't formally articulated until 1983 by Don Page and William Wouters. The moments we identify as different times in our universe appear distinct only from our perspective, not fundamentally different from other universes. The laws of physics tightly connect them to our snapshot. Traditionally, we categorized other times and universes separately. Now, this distinction appears unnecessary. Times are viewed as special cases of other universes. This perspective resolves all paradoxes related to time. Instead of envisioning how the multiverse evolves over time, David suggests a consistent approach of considering how time unfolds within the multiverse. Other times are merely specific instances of other universes. Some of these universes, according to Deutsch, resemble our own, now so closely that we interpret them as part of our universe's history rather than separate universes. For us, these instances are not located somewhere in space, but on our timeline. However, in reality, our timeline represents a distinct universe at every moment, according to David Deutsch. This is the mechanism of time. If this holds true, it explains why time is so transient and elusive. Considering this perspective, one might wonder how many universes have changed since the beginning of watching this video. If we were to ever discover time travel, it wouldn't spark controversy. Altering the past, such as killing your grandfather, wouldn't create paradoxes, because traveling to the past would mean traveling to other universes, vastly different universes where a person with your genetic code was never born. In this complex choice experiment, the future doesn't influence the past. Photons exhibit interference or a two-band pattern because all future choices already exist. Similarly, all past choices also exist. In the multiverse, all information from the inception to the conclusion of time already exists. In this sense, the multiverse interpretation is entirely deterministic. Every possible event from the beginning to the end of the universe has already occurred, with various scenario variants existing on different probabilistic branches or sections of the multiverse. If several completely identical copies of me and other versions of me exist in other universes, the question arises, which of them then am I? This question presupposes a frame of reference outside the multiverse, in which an answer can be given. By saying, I am the third from the left, you introduce ambiguity. What does third mean? What does it mean to the left? Such terminology implies that there are snapshots of me lined up in various positions in some external space that does not exist outside the multiverse, nor does external time. All existing space and time are within the multiverse itself. The multiverse simply exists and encompasses everything that exists physically. If you have ever wondered what was before the Big Bang or what will be after the Big Compression, you may now lose interest. The multiverse has no beginning or end. Terms like begins and ceases to exist imply the passage of time, which in this context does not exist. The multiverse exists outside of time. Our interest in what precedes or follows all of reality stems from the notion of the flow of time. We exist in numerous variations, in universes called moments. Each version of us is not directly aware of the others, but has evidence of their existence due to the interlocking laws of physics in the various universes. No single, even approximate, illustration can adequately depict the nature of the multiverse. You may ask, Deutsch is really proposing to create an infinite number of new universes at every moment in time, just to explain the pattern of shadows in the slit experiment. Let us clarify that universes do not arise at every moment of time. They already exist. Paradoxically, the many worlds interpretation does not increase the number of entities. Many believe that the many worlds interpretation is not even an interpretation, but the most direct reading of the equations of quantum theory. Attempts to explain quantum mechanics in a different way tend to complicate matters. From David Deutsch's perspective, the many worlds interpretation is by far the most satisfactory explanation of the structure of reality. This interpretation resolves many issues, including philosophical ones. It clarifies the possibility of what we call free will. At the same time, it asserts that freedom is not related to randomness and resolves contradictions. The many worlds interpretation even fills a gap in Darwin's theory of evolution by solving the problem of explaining the rapid development of complex adaptations. On my channel, you can watch a video that talks about the fact that the probability of a particular person being born is incredibly small. The question itself may seem unusual, but within a multi-world interpretation, it takes on a different perspective. With an infinite number of universes, all people who could potentially exist do exist in a multiverse. In one notable exchange, physicist Bryce DeWitt raised detailed technical objections to Hugh Everett's multiverse theory, which Everett successfully refuted. DeWitt ended his argument on a more informal note, pointing out that he simply cannot feel that he is splitting into numerous different copies whenever he makes a decision. Hugh Everett's response sounded like an echo of the argument between Galileo and the Inquisition. He asked, "Do you feel the Earth is spinning?" DeWitt admitted defeat. I hope you found it interesting. Thanks for watching, and don't forget to share your opinion in the comments.